Welcome to Chapter 3, Section 5, the chain rule. This video I'm going to give you a quick introduction to what the chain rule is and how we're going to use it here in calculus. So let's take a look at a couple of these functions here. I've got two functions, sine of x and x squared minus 4. And we can take the derivative of both of these functions. We know that the derivative of sine of x with respect to x is simply cosine of x. And the derivative of x squared minus 4 with respect to x is 2x. But what about the derivative of sine of the quantity x squared minus 4? We don't have any techniques to do this yet because this isn't a product. We're not multiplying the sine of x times x squared minus 4. This is a composite function. This is a function inside of a function. Another way to look at this is f of x is sine of x and g of x is x squared minus 4, and so this is f of g of x. And so we need to figure out a way, how can we differentiate this? And that's what the chain rule does for us. So let's take a look at a simple function first and see if we can come up with a rule that can translate to that function of sine of the quantity x squared minus 4. So let's start with a simple function of y equals 6x minus 10. We could take the derivative of this function, and in fact we know it's simply 6, but we're going to rewrite this. We're going to write this as a composite function. Instead of y equals 6x minus 10, we're going to write it as the composite of y equals 2 times the quantity 3x minus 5. So if we were to write our f and g function, f of x is just 2x and g of x is our 3x minus 5, and so notice we have this 3x minus 5 inside of the f of x, or 2x here. Okay, and you might ask, well, why are we trying to make this more complicated? Once again, we're trying to take a simple function of what we know the derivative is, write it as a composite so we can see a pattern. Okay, so we're taking a simple function to try to relate it to a more complicated function. So if we look at this composite of y equals 2 times the quantity 3x minus 5, we're going to rewrite that using u substitution, saying that, well, this is simply y is equal to 2u, given that u is 3x minus 5. So if we were to substitute in the 3x minus 5 into u in this place, we would still wind up with our original function y equals 6x minus 10. Now let's take a look at a few things here. We know that the derivative of y with respect to x is 6, our original function, dy dx. That's going to be 6. Okay, we already know that. And we know that if we take the derivative of y with respect to u, well, that's just 2, okay, because u is our variable here, and take the derivative, we just keep the coefficient of 2. And if we take the derivative of u with respect to x, it's 3. And you may notice the coincidence that, well, 6 is equal to 2 times 3. And that, in fact, is not a coincidence. That is the chain rule. Okay, this is the chain rule right here, just saying that dy dx, when y is a composite function of x, then you can simply take the derivative of y with respect to u and then multiply by the derivative of u with respect to x. And notice these two du's essentially cancel. And so we're left with just dy dx. Now, I use the term cancel very lightly here because they do not cancel du. Like I said in a previous video, we are going to implicitly define what du really means, and we haven't done that yet. But they don't actually cancel, and I want you to make sure that you understand that. But we can use that term loosely, that they cancel to leave us dy dx. Okay, so let's revisit our function of sine of the quantity x squared minus 4. Well, if that's going to be our function, then let's redefine our function, given that let's make u equal to x squared minus 4. So now we're looking for the derivative of sine u. Okay, so let's take a look at, well, the derivative of y with respect to u. If this is our y function, sine of u here, then the derivative of that with respect to u is just cosine u. Knowing our trig functions here and their derivative definitions, that's just cosine of u. And the derivative of u with respect to x, that's simply 2x, because we drop down the exponent as a coefficient, decrease the exponent by a power of 1, and we get 2x. The 4 goes away because it's a constant. So to find our dy dx, we simply use our chain rule here of dy dx is equal to dy du times du dx. Well, we have dy du, we have du dx. We multiply those two together, so it's just cosine of u times 2x, but we don't want to leave u here. We want to substitute back in the x squared minus 4 into u's place, and we get our derivative of 2x times cosine of the quantity x squared minus 4. Okay, another way to look at this visually, now all of this is perfectly sound and it's following the chain rule formula. Another way to look at this is the inside-outside function. We have an inside function of x squared minus 4 and we have an outside function of sine. Okay, so if we want to take the derivative of the outside function first. And so ask yourself, what is the derivative of sine of blah, whatever it may be, sine of x, sine of u, sine of n, sine of any variable you want. So the derivative of sine of something is just the cosine of that something. So we write cosine of that something, whatever's inside, the entire function in its entirety written right there inside of our outside function after we take the derivative. Then we have to ask ourselves, well, what is the derivative of our inside function? And that's going to pop out as a coefficient. Okay, now that coefficient, keep in mind, don't think of coefficient only being a constant. The coefficient could still be a function of x, and in this case it is still a function of x, being 2x. So you can look at it as an inside-outside function with these composite functions, or just look at the two functions using the u substitution and using our chain rule formula.